Hello and welcome back to Introductory Astronomy. Since Chapter 1, you have been on an outward journey throughout the universe. Now you have reached the limit of your travels in space and time and can study the universe as a whole. The ideas in this chapter and the next are among the biggest and most difficult in all of science. Can you imagine a limitless universe? Or the first instant of time? As you explore cosmology, you will find answers to three essential questions. Does the universe have an edge and a center? How do you know that the universe began with a Big Bang? How has the universe evolved, and what will be its fate? Let's start with this image called the Ultra Deep Field, which was taken with the advanced camera for surveys aboard the Hubble telescope. It is one of the finest photographs of deep space ever made. More than 1,000 galaxies are crowded into this one image, displaying many different types, shapes, and colors. In all, astronomers estimate that the observable universe contains about 100 billion such galaxies. In this chapter, we're going to talk about the universe on the largest scales, the expanding universe, the fate of the cosmos, and the geometry of space. We're also going to tackle the question of will the universe expand forever, and the dark energy and dark matter, and the cosmic microwave background radiation. Here we have a galaxy survey. This map of the universe is drawn using data from the Sloan Digital Sky Survey we talked about in the last chapter. It shows the locations of 66,976 galaxies lying within 12 degrees of the celestial equator and extends out to a distance of almost 1,000 megaparsecs. The largest known structure in the universe, the Sloan Great Wall, is marked, stretching nearly 300 megaparsecs across the center of the frame. There is no evidence for any structure on larger scales. Here we have the results of a deep, quote-unquote, pencil beam survey of two small portions of the sky in opposite directions from the Earth and perpendicular to the galactic plane. In frame B, we see the plot of that information. This plot shows the number of galaxies found at different distances from us out to about 2,000 megaparsecs. Wherever we look on the sky, the instinctive picket fence pattern highlights voids and sheets of galaxies on scales of 100 to 200 megaparsecs, but gives no indication of any larger structures. Therefore, we can conclude that the universe is homogeneous. Any 300 megaparsec square block appears much like any other, on scales greater than about 300 megaparsecs. The universe also appears to be isotropic, meaning it looks the same in all directions, which leads up to what we call the cosmological principle. The two assumptions of isotropy and homogeneity in our universe on sufficiently large scales. Olber's paradox. Olber's paradox says that if the universe were homogeneous, isotropic, infinite in extent, and unchanging, then any line of sight from the Earth should eventually run into a star, and the entire night sky should be bright. This obvious contradiction of the facts is known as Olber's paradox. So why is it dark at night? The universe is indeed homogeneous and isotropic, but it is not infinite or unchanging. Again, if it was also infinite and unchanging, then in any direction in the sky we look towards, it would be bright, just like the surface of the sun. And since it is not, we know it cannot be infinite or unchanging. We have already found that galaxies are moving faster away from us the further away they are. Hubble was the first to observe that, and he came up with this relationship, where recession velocity is equal to h0, the Hubble constant, times the distance. So how long did it take the galaxies to get where they are now? In order to answer that question, we use one of the most basic physics principles, the idea that time is distance divided by velocity. So how long it takes to cover a certain distance depends on how quickly you're moving. Now we know that velocity can be calculated using Hubble's law. So we just replace for velocity h0 times distance. Distances cancel, and we have time as a formula with only one constant, Hubble's law. If we use the constant as 70 kilometers per second per megaparsec, then we find time to be about 14 billion years, the age of the universe. Now, note that even though it appears to place us at the center of the expansion, Hubble's law does not violate the cosmological principle in any way. To see this, let's look at this figure much more closely, which shows how observers in 5 hypothetical galaxies perceive the motion of their neighbors. The top numbers are the distances and recessional velocities as seen by an observer on the middle of 5 galaxies, say galaxy 3. The bottom 2 sets of numbers are from the points of view of observers on galaxies 2 and 1, respectively. In all 3 cases, Hubble's law holds. The ratio of the observed recession velocity to the distance is the same. So Hubble's law is the same regardless of who makes the measurements. So there is no violation of the cosmological principle. If this expansion is extrapolated backward in time, all galaxies are seen to originate from a single point in an event called the Big Bang. So a legitimate question would be, okay, so we move the frame backwards and it all seems to go back to a single point. Where was this point? Where was the Big Bang? And the answer to that is that it was everywhere. Because no matter where in the universe we're located, we will measure the same relation between recessional velocity and distance with the same Hubble constant. So where was the Big Bang? It was everywhere. This can easily be demonstrated in 2 dimensions. Now this is an analogy, okay? We can't really show that in 3 dimensions, so we're going to lower down our perspective to 2 dimensions. Let's imagine a balloon with coins stuck to it. As we blow up the balloon, the coins all move further and further apart. There is on the surface of the balloon no quote-unquote center of expansion. Similarly, galaxies recede from one another as the universe expands. As the coins recede, the distance between any 2 of them increases, and the rate of increase of this distance is proportional to the distance between them. Thus, the balloon expands according to Hubble's law. The same analogy can be used to explain what we call the cosmological redshift. This is the component of the redshift of an object that is due only to the Hubble expansion of the universe. So as the universe expands, photons of radiation are stretched in wavelength, giving rise to the cosmological redshift. In this case, as the baseline in the diagram stretches, the radiation shifts from the short wavelength blue region of the spectrum to the longer wavelength red region. Now, I know these concepts are hard to comprehend and not at all intuitive. A full description requires the very high-level mathematics of general relativity. However, there are some aspects that can be understood using relatively simple Newtonian physics. We just need the full theory to tell us which ones. So let's continue. There are two possibilities for the universe in the far future. Number one, it could keep expanding forever. And number two, it could collapse. Assuming that the only relevant force is the force of gravity, which way the universe goes depends on its density. And density in physics can be calculated very easily by using this formula right here. The Greek letter rho represents density, so rho is equal to mass divided by volume. So here we have those two basic model universes represented on a graph, which is the distance between two galaxies as a function of time in each of the two basic universes that are also discussed in the text. A low-density universe, if we have that scenario, it would expand forever. And if we have a high-density universe, then we're going to have a collapsing universe. The point where the two curves touch represents the present time. So in our time, it could go either way. We could be at the low-density scenario where the universe expands forever, or the high-density scenario where the universe collapses. There is also what we call the critical density, and that takes place between collapse and expansion. At this density, the universe still expands forever, but the expansion speed goes asymptotically to zero as time goes on. Given the present value of the Hubble constant, the critical density is approximately 9 × 10⁻27 kilograms per meter cubed. This is about 5 hydrogen atoms per cubic meter. If space is homogeneous, there are 3 possibilities for its overall structure. Number 1, it could be what we call a closed universe. This is a geometry that leads to ultimate collapse. It could be a flat universe, which corresponds to the critical density scenario, or it could be an open universe, which corresponds to the expansion forever. These 3 possibilities can be described by comparing the actual density of the universe to the critical density. Astronomers refer to the actual density of the universe as the capital Greek letter omega, and to the critical density as omega naught. So we can now describe the 3 possibilities in terms of this variable. If the true density of the universe, omega, is less than omega naught, then we have the open geometry scenario. If omega is equal to omega naught, then we have the flat geometry. And if omega is greater than omega naught, we have the closed geometry scenario. Let's take a look at what is called Einstein's curveball. If we live in a closed universe, a beam of light launched in one direction might return someday from the opposite direction after circling the universe, just as motion in a straight line on the Earth's surface will eventually encircle the globe. Your book goes into great detail in describing the three geometries. So the three possibilities for the overall geometry of space are shown here. The closed geometry is like the surface of a sphere. We have what is called a positive curvature, or the Riemann geometry. And as you can see, the sum of the angles of a triangle are greater than 180 degrees. We also have the flat geometry, which corresponds to what we call the Euclidean geometry. It's where the sum of the angles of any triangle are 180 degrees. And we also have the third possibility that is called the open geometry, that looks kind of like a saddle. That corresponds to what we call the negative curvature, or the Lobachevsky geometry. In this case, a triangle on this surface has a sum of angles that is less than 180 degrees. So as you can see, it's very important to figure out what the actual density of the universe is, so we can compare that to the critical density, so we can figure out the corresponding geometry. Once we know the corresponding geometry of our universe, then we can figure out the fate of our universe. Study chapter 26.1 through 26.4. Be able to state the cosmological principle and explain its significance and observational underpinnings. Be able to explain what observations of the dark sky tell us about the age of the universe. Describe the Big Bang theory of the expanding universe. And discuss the possible outcomes of the present cosmic expansion.